I wanted to spend like 2 lectures at least on density metrics because it's a pretty important topic if you want to study open quantum systems. Um, it's really useful to study mixed states, which is generally the case whenever we are doing real world applications. Because generally we don't get a system where we have like specifically just one particle unless we manufacture that system, which we do in research labs. But generally the case that you do get more than one particles, and definitely more than one states. So if you have a collection of them, mixed state approach or statistical mechanics approach is necessary to tackle with to solve these problems. So yeah, in last lecture as well, I think I mentioned this that this is like the basic motivation why we are going for density metrics as opposed to just normal state vector formalism that you guys start with when you're learning quantum mechanics. So I think today we will just learn about what is density matrix formalism only for a pure state. I think in the last lecture I motivated what is pure state and what is mixed state. Um, just to say in one line again, pure state is just when you have complete information about your system. That is, you know all the eigenvectors and all the eigenvalues that are possible when you do measurement on that system. And the probabilistic nature of um, comes in pure state when we are talking in terms of only like the probability comes only in the measurement process. But when we are talking about mixed state, which is like a collection of states or collection of particles, then the probability is mainly in the choice of the system. So the probability there is mainly classical, like it has an analog to classical because like it comes from statistical mechanics. Um, but in this case, in pure state case, whenever we are talking about probabilistic nature, it mainly comes from quantum mechanical principles, and that is the probabilistic nature of the measurement itself. So even if you have just one system which has n number of eigenstates, you still have a probabilistic outcome after your measurement because there is the probability specifically associated with all the eigenvalues and all the eigenvectors, which is the square of the coefficient that is associated with that eigenvector. So today we will only talk about pure state, but the extension to mixed states is fairly straightforward. And if you see the video that I sent on group last week, I will be following very similar steps. So, and it also has the channel. Professor M Does Science is the channel. That is, I think, um, a professor. There are two professors in Cambridge, UK, who run that channel, and um they want to simplify the quantum formalism for students. That's why they have these videos. So in their at their channel, Density Matrix Formalism has like 3 videos. The first video talks about pure state versus mixed state. The second video talks about density matrix formalism for pure state, and third video talks about density matrix formalism for mixed state. So I think everything you need to know, all the basics that you need to know for density matrix formalism are sufficiently described in those videos. So I have already put a link on the Telegram group. So please watch them if you want to get like detailed information, or just a good review of whatever we are going to discuss. Um, that being said, there are like 13 people here. I leave, I guess, the entry open and maybe start the lecture in a minute or so. Is that okay, Nathan sir? Since you are here today. Okay, yeah, we can wait for maybe till 4:10. I'll wait till 4:10 and then I'll start. That should be 10 minutes should be sufficient. So yeah, we can do quantum mechanics with revised notes. Yeah, that's fine. We have been doing quantum mechanics with state vectors for a long, for as much as we have been doing quantum mechanics. So um, yeah, the revision of last lectures, I want to do maybe after this topic, because after this topic there are like, so the things that we did in like last 4 lectures. First lecture was just introduction. So second lecture was harmonic oscillator. Third lecture was two-level systems. The fourth lecture was based on lasers and how we do quantum mechanics formalism. Uh, what's the mapping with linear algebra? That was the fourth lecture, and this lecture is going to be density matrix formalism. So, including these four, like 5 lectures, if you have any doubts, please, this is like the correct time to ask. There is also one assignment, one short assignment today, for deriving some properties of density matrix. So you have to derive like 4 properties. They are pretty straightforward. They are also derived in those videos. I would recommend you try it yourself first and then see those videos, because they go step by step in those videos. If you don't get it, then you can follow the steps in the videos. It's fine. But those properties are like essential to understanding density matrix formalism. So they play a key role in everything that we do with density matrices over this course. So make sure that you know how to derive them and keep them handy with you all the time when you're doing this formalism. Okay, 80 people are there. Um, I guess I will start. So yeah, today, like I said, I want to talk about density matrix formalism. Um, Last lecture I introduced what is density matrix. I will reiterate that density, like we generally do quantum mechanics with state vectors, which is like the wave function psi. When you're doing quantum physics with state vectors, there is a limitation that when you do open quantum systems, you are stuck with certain aspects that are non-trivial when you are doing quantum physics with this formalism. So that's why the motivation comes to apply or to adapt a different formalism other than the state vector formalism, which is not very difficult to go from one formalism to another formalism. So I will show you how we go from one formalism, which is already known formalism to us, that is the state vector formalism, going from that to density matrix formalism. That is the crux of like what I want to deliver today in this lecture. So I guess let's start. Um, so today I will only talk about pure states, but there is a video which I talked about already. which is does science video, and that uh, has the extension. The third lecture on density metrics on that channel has the extension to mixed state using density metrics. So those who are interested, those who want to thoroughly do this topic, please see that lecture, which is like a, I mean, I say lecture, but it is like a 10-minute video, and it will clarify all the concepts regarding how to use density matrix formalism for mixed state. But today we'll just focus on pure state. So we will focus on a pure state, which is very familiar to us, which is like a two-level system state. In two-level systems, like basically you just now have two levels, which are the two eigenvectors, and associated coefficients are C1 and C2. So basically, if you have an operator, then if you operate it on psi, you will get an eigenvalue and the state vector again. So this is like the measurement process for the operators, but this is the state vector for us, which is a two-dimensional case. So it has two basis vectors, u1 and u2, and with each coefficient c1 and c2. And the probability is given by just c1 square, mod c1 square, or mod c2 square as the measurement probability. Um, if you see, the state can be either in c1 with c1 square probability, or in either in u1 with c1 square probability, or in u2 with c2 square probability. So this is like well known to us, like a two-level system superposition state, and this is the wave function for that. So now if we want to study this using density matrix formalism, then how to write it? Then the construction is such that we take an outer product of psi with itself whenever we are forming the density matrix using state vectors. So this is a pure state. So pure state has a um, well-defined uh, vectors, which is like well-defined form in terms of the basis vectors. And if you want to construct a density matrix now, you just take an outer product of that state vector with itself. So in quantum physics, whenever we want to manipulate vectors, there are like generally two operations that we do. Even in vector spaces, there is either inner product or outer product. Inner product gives you a scalar because A dot B is a scalar, which is same as taking uh, psi psi. And outer product is, this is very obvious, but still I wanted to mention this, that this is now a matrix. When you do a product like this and you get a matrix out of it, which is an operator. So this row is an operator. If it operates on something, it will give you a corresponding value, which is what we get by all the eigenvalue equations. So this is like the eigenvalue equation. So if you operate it on anything, we will get some value and then again that vector. So um, this is how you construct a density matrix for a pure state psi. So we'll construct it for this particular pure state. But before doing that, if you see the form of this density matrix operator, the form is similar to the projection operator that is used in quantum physics. But so to motivate what is projection operator and why is it so important, we will first take a little detour and see what is a projection operator and what properties it has in quantum physics. So as I said, if you take an outer product of the state vector with itself, then you get a projection operator because this projection operator has this form, which is outer product of psi with psi. So what is a projection operator? It is basically an operator that is defined as if you operate it on a wave function, you'll get back the wave function. So it is necessary to understand this operator because whenever you are doing wave function collapse, which is Wave function collapse is something that happens when you're performing a measurement. So if you are performing a measurement, if you're observing an observable, like you're operating on a wave function, mathematically speaking, then there is a wave function collapse. What does that, what do you mean by wave function collapse? Is basically the state, um, the basis of the state vector. The state vector is originally described in a certain basis. Like in this case, we described psi wave function in the basis of u1 and u2. So u basis. So psi was in u basis. So initially, all we represent each vector, each state vector or each system in certain basis, and the operator has its own basis in which gives you how to construct that operator, because each matrix basically has eigenvectors, and each matrix then has a basis set. So um, since our operator is a matrix in quantum physics, that's why each comes with its own basis set. So now when you're doing performing a measurement, what you do is if an operator A operates on psi, and you get some eigenvalue with the psi operator again, with the psi state vector again, then what you're essentially doing is you're taking a projection of your state vector on projection of your basis vector on another basis set. So when you're performing this projection, you're basically changing the basis, or you can say in other words, you're making the basis same for this these two operator and state vectors, such that this operation now can be performed. So the change of basis or wave function collapse or projection onto different bases, all things kind of have the same meaning in quantum physics, and it is just a way to change basis or a way to project onto some other basis is like is the most essential, one of the most essential topic in quantum physics, and to understand it intuitively as well, it's really important. That's why we will consider the formalism in terms of projection operators first, because these operators are essentially what you use whenever you do change of basis. So like if you want to go from stationary frame to a rotating frame, what you do is do a change of basis. And the change of basis projection operator will be the operator for the rotating frame. So if you want to go from stationary frame to rotating frame, there is a specific projection operator that you need to apply to your state vector so that you can go from one frame to another frame. Basically, if you want to do a change of frame or a transformation from one basis to another basis, you do need this projection operator because you do need projections on certain axes. And this is also true in vector spaces, that if you have like a vector A and vector B, then the projection of A on B is given like this, and that projection is just A dot B. So how much of A is present in B if you take like a projection on another vector? So that is like, this essentially comes from vector spaces, but intuition wise and physics wise, it has like a lot of importance to understanding uh, how we do change of basis, how we do change of frames. And since there is a Einstein's famous relativity principle that even if you change frame, the physics doesn't change. So that gives us the liberty that we can use this um, to our understanding, and then we can utilize the fact that we can do change of frame, and by change of frame we do get simpler equations, we do get simpler solutions, and the formalism gets more straightforward in a certain frame. So that's why we go from one frame to another frame, and to go from one frame to another frame, or to go from one basis to another basis, we do need a projection operator, we do need a projection step, and that is like the very crucial step in quantum physics all the time. Because we are going to do this step because rotating frame approximation or rotating frame transformation is something that we are going to do when we are doing the optical block equations. So just remember that whenever we are changing from one basis state to another basis state, or whenever we are changing from one frame to another frame, we have to do this projection. Okay, so if we consider again state vector psi, then we already know that the state vector has to be normalized. So the normalization condition is like this. Um, so the inner product with itself has to be one. That is that is like the normalization condition for any wave function to be uh, a valid wave function. So how we define our projection operator is exactly same as the density matrix, that it is an outer product of psi with itself. So now if we operate this psi on a state phi, which is a different state, so then just to make the distinction clear, let me make this a capital phi. So if this is the state now that we want to measure on, so this is now our state, and this is the projection operator. So projection operator will take you from this state or the basis of phi to the basis of psi. So how does it do that? Is if we operate the projection operator on the state phi, then we just substituted the form of projection operator here, which is the outer product of psi with itself. If you see, then if it operates on phi, then what we get is this quantity is a scalar, which can be represented as C of phi, which is basically a coefficient that you get when you have a projection. So this is a scalar quantity, so that will come outside, and this is a ket vector, so that remains as it is. So basically what you get when you have a projection in the psi basis on phi state, which was earlier in the phi basis, what you get is a projection onto psi basis. So the resultant final vector that we have is in the psi basis. So we have transformed from one basis to another basis, and we do get the weightage or the projection by doing this change of basis by this factor C phi. So this is how projection operator is defined, or this is how projection operator is used when we are doing change of basis. So we got the projection of psi on phi, and the overlap is quantified by C phi. So this is the overlap between phi and psi. And if they are orthogonal, then this will be 0. If they are parallel, it will be 1. So if they are orthogonal, then C phi is 0. Basically, by orthogonal, I mean if they are perpendicular. And if they are parallel, then C phi is just 1. So if you have the same state that is projecting on the same state, then you'll definitely get just 1. If you have a perpendicular state, if these two are orthogonal, then you'll get just 0. So there is you can't project on. So basically, you can't project x-axis on y-axis because these two are orthogonal. So similarly, but if you have like a diagonal vector going, let's say y is equal to x line going through y-axis and x-axis, like starting from the origin, then you will have projections on both y-axis and x-axis because it has components along x-axis and y-axis. So basically, this gives you the component along a specific vector or along a specific basis. So that's why it's called a projection operator, because it projects on that basis and gives you the component along that basis, which is always what we want. Because in quantum physics, whenever we are doing measurements, we are basically taking projections along a specific axis. And that is what we quantify as the value. The measurement outcome that we get is basically a projection along a certain axis. And whenever we are also doing probabilities, that those are also the squares of those coefficients, which are the projections essentially. So this projection operator basically what it does is it projects one state on another state. Okay, and the measurement process, like I said, measurement process is defined in quantum physics as the collapse of the state wave function, basically its basis, on operator eigenstate, which is another basis. So it's a change of basis. And in other words, it is projection of an operator basis on the state vector basis. So it is change of basis done by the projection operator. And like I said, it is the same in vector spaces as well. So literally mathematics wise, you are doing just inner product, and you're seeing the component along a specific direction. And the component if you're uh, if you're interested in just the direction, then this can also be written like that. But so what are the properties of this projection operator then? So there are, like, I guess, 3 or 4 properties that are really important here. So the projection operator, I guess, is defined itself as an operator where the square of a projection operator gives you the same. And from this property, actually, and it is very easy to prove if you just take if you just operate it on any vector, then you'll get that it is again a projection operator. Like these two things will give you the exact same. Uh, so basically, if you solve for this, you'll get the exact same thing. So the project square of the projection operator is again a projection operator. Um, and this is the property is called as being idempotent. And the second projection will not give you anything. That is kind of intuitive, because if you are taking a projection on a certain basis, then now you have transformed to that basis. And if you are taking projection again, then basically you're transforming into the same basis. So then you'll again get the same value. So if you are projecting basically x-axis on x-axis, you won't get anything new. So you will get just one. And that is always like the property of projection operator, that if p square is p, that directly gives you that p has to be plus or minus one. So then if you operate actually, so the p here is the value. So P has to be plus or minus one. And actually from this, from projection operator's definition itself, you get like symmetric and antisymmetric states, which is like if P is plus one, then it's a symmetric state. If P is minus one, it's a antisymmetric state. Or so there are like identical particles, symmetric, antisymmetric wave functions. Everything comes from just this projection operator. That's why it's like a really important thing. But yeah, I'm not going to emphasize much more on this because eigenvalues. Yeah, P are the eigenvalues. So you have either plus one or minus one. So lambda can be either plus one or minus one. And I think even Nitin sir in his lectures, I think motivated this point a lot, that in atomic physics, you get symmetric, antisymmetric states, and you get like in two-level systems, especially. You get these states, and you get identical particles. You can understand all that formalism just by understanding the projection operator. That's why it holds a really important value in quantum physics. So this is the first property, which is kind of like the definition of projection operator, that if you square it, you'll get back the same. Second property is being Hermitian. So Hermicity is the second property, and if any operator is Hermitian, you already know that the eigenvalues are real. So that is also another requirement in quantum physics, that whenever we are choosing an observable, which is an operator, which is basically a matrix, then that matrix or that operator has to have like real eigenvalues, because in the real world, when we are going to do any measurement, we can't have like imaginary outcomes. Although um, there is a way to handle imaginary eigenvalues, and there is a way to do quantum physics even with non-real eigenvalues. But that is something that is, I guess, called as a non-Hermitian quantum mechanics, and that has literally like a separate formalism, or that is like pretty complicated. That should be like the next step after you have understood everything about Hermitian quantum mechanics. Then only you should proceed and do non-Hermitian quantum mechanics, because that involves, of course, analysis of quantum systems which are open, and like that. That is a little more complicated. But whenever we are doing Hermitian quantum physics, the basic formalism is clear. So this Hermicity property is actually, if you take a dagger of projection operator, you'll get back the same operator. So that is like the property that projection operator has. And in addition to that, all the eigenvalues are also positive. So if you take, whenever we are taking an eigenvalue of the projection operator, we can make a statement that they have to be because using this, the fourth property comes that whenever you want to express any ket vector in terms of a projection operator, you can do that. Basically, in vector spaces, there is a property that if you want to express any ket in terms of parallel and anti-parallel, parallel and perpendicular components of that vector spaces, then using projection operator, you can do that. And using projection operator, the way to do that is if you have any vector that you want to describe, which is phi, then that vector can be described by in terms of projection operators and its own basis by this equation where you get projection operator times psi plus 1 minus projection operator times psi, which is with eigenvalue 0 and eigenvalue 1, which we already discussed that it can have two eigenvalues. This is sort of, I mean, this property is a little complicated than the other two straightforward ones, but we will maybe understand it better in terms of, I guess, in vector spaces, if you consider this property, then this is much simpler that this is like a Fourier case. Because in Fourier also, we say that there is a certain basis set and you can always express anything in terms of that basis set. Or if you have linearly independent elements, then you can express your entire span of your vector space in terms of your basis states. And that is essentially what you can do even here, but using projection operator, that any ket in your present vector space can be described or can be formed in terms of just projection operators and any other psi, which is parallel or perpendicular to it. So, but we are not going to talk a lot about this property. I just wanted to mention it once that this is another property of the projection operator. But mainly understand that the form of projection operator is like this, and the form of projection operator is really similar to what we are going to see, especially in terms of these two properties, what we are going to see in density matrix formalism. Because density matrix formalism also you get such properties, and because of that or vice versa, we say that density matrix operator is also a projection operator. So let's go back to density matrix formalism. This was just a slight detour because I wanted to explain that projection operators carry a lot of importance in quantum physics, and you can imagine now density matrix as a projection operator, because literally the definition is exactly same as the projection operator definition, which is the outer product of state vector with itself for a pure state. So this is the definition of density matrix again. Which is the same. Now we know that it's the same as projection operator definition. So for a pure state, again, to remind you that we have now the full knowledge of the system. What do you mean by full knowledge is if you do any measurement, you already know what are the possible outcomes, and the probability of that outcomes can be determined by the square of the coefficients. So you have a superposition state and you basically have all the knowledge of your system, that all the eigenvectors that are possible if you do a measurement and if you find out eigenvalues. So in your measurement process, the probabilistic nature is inbuilt. So it's like mainly a quantum mechanical thing whenever we are talking about pure states. And whenever we are talking about then mixed states, which is like the incoherent or like the population, like the mixed state is basically a collection of particles either or collection of states. And there the probabilistic nature also comes from classical statistical mechanics. But right now we are just talking about pure states. So we have like the full knowledge of the system, which won't be the case if we are talking about mixed state. Because in mixed state, we have partial knowledge about the system. So since we are talking about pure state, we know the system fully, we have the complete information about the system. So now what are the properties of the density matrix? So let's start with operating density matrix on a state vector. So this is the definition of density matrix. So it's an outer product with itself. So if we operate it on a ket, then these two together will get normalized because we have chosen a normalized basis. So this will be 1. so you'll get 1. So if you operate it on psi, you'll just get 1. You'll just get the psi vector back. If you then square it and then operate it on psi, then if you take a square, then it is rho times rho, and we know that rho is same as rho dagger. So then if we take this operation, then if we multiply with this, then we again get back the same. So like we were talking earlier, that rho square is same as rho, which we saw in projection operator as well. So the eigenvalues can be just plus or minus 1. So basically you get this property, which we saw even in the case of projection operators, that the square is the same as the projection operator itself. So, and you won't get this when you are doing a formalism, which is different. Like in mixed state also, there are these properties, and there is a mapping that you can do from pure state to mixed state. And like I said, those who are interested, there is a great video for mixed state using density matrix formalism on YouTube. So another property is, so whenever we are talking about matrix elements, so if we are doing density matrix formalism and we are doing quantum physics with that formalism, then you have to be accustomed with the fact that you are always talking about matrix elements. So if you are talking about a matrix, which is a square matrix, then in that matrix, you always have diagonal elements and off diagonal elements. So what are those two? So then, because each of them carry a certain meaning in quantum mechanics, if you develop a row, which is a density matrix for a state vector, which is, let's say, a state vector is psi, which is a superposition of all different u bases. Then it's a summation over all the coefficients and the u basis. So in two-level systems, what that will be is the psi is, in two-level system, psi is C1 U1 plus C2 U2. If you have that system, then for that system, if you want to see, and we looking at this statement, actually we can say that the psi is in u basis. So if psi is in u basis, we also want density matrix to be in the same basis. So if we want that, then we can create it by doing this operation. So if you want to say that, if you are interested in a specific matrix element, then you have already chosen a basis, of course, which is orthonormal, because which means that if I is not equal to j, it is 0, and if I is equal to j, it is 1. So basically, if these vectors are orthonormal, so the basis vectors are orthogonal to each other, and also they are normalized. So that's why that's what you mean by orthonormal. So the basis is orthonormal. And now if you want to describe the projection of rho on this basis, then you'll get just you'll get a coefficient in that specific basis. And how to carry out that is, if you just do so this is the definition. So if psi cross psi is the definition of rho, so then if we do uj, then this gives you ci and this gives you cj star, because ket, this is the coefficient of ket vector, so this is the projection on, so let's say like this. So this is a projection on the u basis, and this is again another projection on u basis, but the dagger of the same. So you get rho ij as ci cj star. So, and then if you construct a matrix for this operator like this, then the matrix will look like this, in which all the diagonal elements are actually the multiplication of this of any coefficient with the same coefficient. So that will give you the square. So all the diagonal elements are actually ci squares, and all the, so this is diagonal, and all the off diagonal elements are CICJ star. This is the form in which we get this density matrix. So this is how we construct density matrices for any state vector given psi. So for our two-level system, the state vector is pretty simple. It is C1 U1 plus C2 U2. So now if you want to construct a density matrix for this, then the density matrix is also straightforward, which is C1 C1 star, basically this form. So it has two diagonal elements and two off diagonal elements. What the diagonal elements specify is populations, because whenever we take squares of these coefficients, actually I should say mod ci square, because it can be I can be 1 or 2. So if you take C1 square, that will be the probability of being in state 1. If you take C2 square, that will be the probability of being in state 2. So you can also say in terms of populations that how much of the population is in the state 1 and how much of the population is in the state 2. Because if we have a two-level system where we are now talking about, let's say, electronic ground state and excited state, then whenever we are talking about the diagonal elements of that density matrix, then we want to specify basically what is the population in the first state and population in the second state. So then if we want to talk about populations in density matrices, we will always talk about the diagonal elements. And what are the off diagonal elements then? The off diagonal elements basically tell you how much of the two basis vectors are correlated. So how much of U1 is correlated with U2 and how much of U2 is correlated with U1. So that correlation, which is also termed as coherence. So this coherence is something that you can understand from the off diagonal elements. So how much, if they are not at all related, then they are basically independent of each other. It's not a superposition state. It's not an entangled state. Then you'll get the off diagonal elements as 0. So if you have rho ij equal to 0 when I is not equal to j, then you can consider that the two then you can consider that there is no entanglement. But if the off diagonal elements are not 0, then there is an entanglement or there is a superposition between the two states, two basis vectors U1 and U2, and you can say that these two are correlated. So off diagonal elements tell you how much of the two basis vectors or any number of basis vectors are correlated with each other, and how much and the diagonal elements give you the populations or the probabilities of finding each one. So that's how we construct a density matrix for a two-level system, and this is kind of the meaning behind each component in the density matrix, because there are like four density matrix components, density matrix elements, and each one of them, the diagonal ones are populations and off diagonal ones are coherences. So this is the language that we will talk in terms of whenever we are dealing with density matrices. That if I am talking about diagonal elements of density matrices, then I'm always consider that I'm always talking about populations in specific states. And if I'm talking about off diagonal elements of density matrices, I'm talking about how much the two states or any n number of states are correlated with each other, or how much of superposition is there, and how much overlap is there between different basis vectors. So this is how you construct density matrix for two-level system. Another property is hermicity, which is the same as what we saw in projection operators, and again, it important same as projection operators. So these are like the properties of density matrices. But now the main question is, if we now understand density matrix, then how to do quantum physics with that? How can we proceed and do quantum physics in the density matrix formalism? That is like the next question. So yeah, the main question is uh, how to do quantum mechanics now with this formalism, because we are always accustomed to doing with state vector formalism. And we will now go from state vector formalism to density matrix formalism. And the mapping is pretty simple. So And these, like the boxes that I have colored in red, are the ones that I want you guys to derive, because they are like the derivation is pretty simple. And like I said, the video also goes step by step into the derivation. And once you do it by yourself, once you do by hand, then you get to appreciate how powerful this formalism is and how simple these properties are if you are going to derive them. But I will just tell you the four properties, which are like the basic properties that, or like the basic operations that we need to do whenever we are doing quantum physics. So in state vector, we are always used to the normalization condition that the inner product of psi with itself should be one. That means basically the probability has to be one if we are searching along the entire Hilbert space. So, uh, and for any wave function to be real or any wave function to be valid, it has to be normalized. So that is like the fundamental thing while choosing a wave function or while choosing a state vector. So if you want to say exact same statement, or if you want to convey the exact same information using density matrices, then we will say that the trace of the density matrix has to be one, because the trace operation in matrices is basically the summation of all the diagonal elements is the trace. So if you are taking a trace of any matrix, you're basically summing all the diagonal elements that are present in that matrix. So I have already kind of motivated here that all the diagonal elements are populations. So you can kind of guess why this is true, because if you sum all the populations together, then they have to sum up to one. Or if you sum all the probabilities, they have to go to 100%. They have to go to one. So this is that is kind of the logic behind this, that the trace of density matrix has to be one. And this is how we will write the normalization condition when we are in the density matrix formalism doing quantum mechanics. But it conveys the exact same information. So these two statements actually give you the exact same information, that the wave function that you are having is basically normalized. But there is a really easy way to prove this, and this you should do it by yourself. And this is like the assignment for this lecture, that you should prove these four properties starting. So this should be the starting point, and this should be the to prove. So you want to reach this statement by starting from this statement. And this is always the case in all the four properties. You have to start from the state vector and then go to the density matrix. So first is the normalization condition. So this is the first case is how we write normalization condition in density matrix. Now, if you want to study, if you want to say expectation value, so we take expectation value of an observable. That is the value that is most probable value. So if you take an expectation value of of a observable in a specific state, in a specific basis, then that is defined as just this in the state vector formalism, that you take an expectation value. Basically, you're sandwiching A in between the two. And you know how to solve this in matrix form and also in integral form, which is like the original Schrodinger's equation form. So you can, yeah, like I mean, we have been talking about matrices a lot, because this is like the Heisenberg way of doing quantum physics. And there is also Schrodinger's way, which is like using integrals and stuff. So you can also define in terms of just that, but the notation is the same. We are using Dirac's Bryant-Kate notation. And in that notation, expectation value of an observable is written like this. So if you want to convey the same information now using density matrices, if you have constructed a density matrix, how will you find out the expectation value of an observable? That expectation value is now given as the trace of the multiplication of the density matrix with the operator. So actually A is also a matrix and rho is also another matrix. So if you multiply these two matrices and take the trace of that product, then that will give you the expectation value of the observable that is necessary for you to find out what is for your specific system, for your specific observable, what is the expectation value. so that you can get by just this equation. So again, this equation you have to start, from here and then prove this. So this is the assignment for this lecture. I mean, after this lecture. So the third property is finding a probability for the measurement outcome. So the probability for a measurement outcome, we say that what is the probability to get a specific eigenvalue. We use projection operator, and finally we land up in the probability where we get like coefficient square. So if you want to convey the same information now using density matrix formalism, then how will you convey is you will have to take a row and have the product with a projection operator. Then that projection operator's product, you have to take the trace that will give you the probability. So now instead of row, so actually this comes directly, the property 3 actually directly comes from property 2, because you are taking basically expectation value, but you are finding out probability now. So there is a way to go from 2 to 3, but still it is kind of pretty simple that you have to take traces. So whenever we are talking about probabilities, it kind of makes sense that we are always taking traces. Um, when we will talk about, let's say, correlations and coherences, then we will talk about the off diagonal elements. But generally, if we are talking about the populations or the probabilities, we generally do take traces because they are the diagonal elements that we are interested in. So if we now know the system completely in terms of density matrix formalism, like we know the expectation value of observables, we know that it is normalized, we know that what's the probability of finding a specific state. Then the next step is the time evolution of the system. So how do we write time evolution in state vector formalism? Is just the Schrodinger's time dependent equation, which is given as I h bar d psi by dt is equal to h times psi. So h is where h is the Hamiltonian. And if you want to write the same thing now using density matrices, you just get minus I by h bar, I guess. So I think you get minus I by h bar. There is a possibility that the h bar is in the numerator maybe, but ignore like the constants. Like the constants are just there so that whenever we are doing experiments, then at that time those constants will be really important. But otherwise, what's important part here is the commutator. So uh, the time dependent derivative actually is equal to the commutator of your Hamiltonian with the density matrix. So this also simplifies our life a lot whenever we are doing quantum physics with the density matrix formalism, that you just now have to take commutator of Hamiltonian with the density matrix, and then you will get the time evolution of your density matrix completely. So this is actually these are the like the four properties, or these are like the four fundamental operations that you do in quantum physics to derive all the information about your system's current state and its time evolution. So this is how we do quantum physics with state vectors, and this is how you go from just state vector formalism to density matrix formalism by just these four equations. And if you know these four equations, then you can do quantum physics in density matrix formalism. So it is actually very straightforward to go from one to another. It's just that you should derive it once by yourself, the specific properties of going from here to here and or from here to here, and first four properties. So these are like the four main properties of density matrices in terms of doing quantum physics. And you should know how you got there, and then once you get there, you should remember that these are like the properties that you guys have to keep in your tool set whenever you are going to do density matrix formalism. So this is actually like the entire point which I wanted to convey for pure state. So this is the density matrix formalism. for pure state. Now, if you have a mixed state, you will have incoherent superposition, where you will have basically many particles together or either many states together. And then the formalism still remains the same. Like if you see the equations, the final equations that come out to be for pure state and a mixed state, they are really similar. I guess I have them. Let me just check if I have them. Um, so these are the properties. So normalization, yeah, these are what we saw just now. If the normalization is given like that, expectation value is given like that in two formalism, state vector and density operator, and time evolution is given like that in both cases. So, but do we have mixed state and pure state comparison? Maybe we don't have, but that is fine because that is there in the video that I sent. So, but I am not going to explain density matrix formalism for the mixed states. The only reason being that that kind of will confuse you if we start with that. So instead, what I wanted to do was make you familiar with the density matrix formalism for just pure states, because that is what we will start with whenever we are doing optical block equations, which is the derivation for the light atom interaction, which is the seventh chapter of Foot, which I'm going to follow. So, but for that, you will need to first be confident with using density matrices and doing quantum physics. So, either do like one or two problems with density matrices. They are like, of course, available on internet. Their density matrix formalism is pretty well known, and I have also shared one PDF on group yesterday. Like I think maybe in few hours back, that that PDF also has a lot of information about density matrices, and it motivates you why they are required and what are all the properties. Again, it summarizes all the properties, and it also gives you for the mixed state, and it also gives you the historical development of how density matrix formalism topic was derived in like 1927 or something. So that PDF is actually pretty comprehensive. So that should give you like clearer idea about why density matrix formalism is important and how you can think about it for your intuition in doing experiments. So, but density matrix as far as the DM formalism is concerned, this is what I wanted to cover for pure states. And the assignment for you is, I'll share this lecture note at the end of this lecture. And the assignment for you guys is basically derive these properties starting from the state vector formalism and going to the density matrix formalism. Once you derive these, you will be pretty comfortable with density matrix formalism. You'll kind of have a good idea set in your head that how we can use density matrices. And essentially, I think you just have to remember the form of this matrix, because this is the one that we are going to use a lot. So this is the two-level density matrix that we will always use, where the populations are on the diagonal elements and the coherences are on the off-diagonal elements. We will later also see the block vector or block sphere formalism, where we can visualize these vectors. We can visualize this density matrix, and by just seeing the sphere and where is the vector pointing along that sphere, you can directly say exact state of that system, which is like a really good way to imagine a system if you have a two-level system, and that simplifies our life for all the explanations that we need to do for precise information, or we don't need to even write down any equations. By just looking at that sphere, which is called as block sphere. Um, so this sphere I'm talking about is block sphere, and this is what we use to visualize two-level systems. But I will talk about it more when we are done with optical block equations. While imagining their solutions, while seeing the solutions of optical block equations and seeing how the system develops and evolves, time evolves, and what the solution means. We will plot it in Blocksphere, and I will also show you how to use that using, or how to demonstrate that using Python as well. So it is kind of a course where in the second half of the course, I will also do a Python session where I will show you like some codes that we can run together, and then give you maybe one coding assignment when we reach that stage. And that all will be done in Python using a Qtip package, which I mentioned when I was going over the course overview. So this is something that we will do using coding as well, which is uh, literally done in day-to-day lab in the research field right now. Using Python's Qtip package, we solve open quantum systems. We use the density matrix formalism to find all the eigenvalues and eigenstates. We use the master equation. So everything is done using like just the one package in Qtip, which is in Python. So we will talk about that. We will also do coding in that in the second half of the course. But first, we will have to do the derivation of optical block equations, which gives you how light and atom are interacting. So that brings me to the last point of today's lecture, which is like the overview of what we did till now. And if you guys have any doubts till now, because next lecture, I think I will start directly with like the first line of the chapter 7 input, which is how it develops the light atom interaction model, where it takes light as a harmonic oscillator and it takes atom as a two-level system. And if these two are interacting, then what is the Hamiltonian that you get? First, we will write down that Hamiltonian. Then we will see how the dipole interaction term comes in when we are talking about light atom interaction. And then after understanding dipole interaction, we will write down the Hamiltonian. After writing down the Hamiltonian, we will solve it. We'll find the eigenvalues and eigenvectors. Then we'll see how it time propagates. Um, so we'll see the time evolution using the Schrodinger's time-dependent equation. And all that requires these four things, which was the reason why I spent so much time on these four things. First is light as a harmonic oscillator, which was covered in the second lecture. Second is two-level systems. Atom as a two-level system is an important formalism that is required for this derivation. The third thing that I talked about was lasers. In the last lecture, I talked a lot about lasers and how you can understand stimulated and spontaneous emission. Then we also talked in last lecture about how we do quantum mechanics. What is the formalism? Like writing the Hamiltonian is the literally the first step. Then solving that Hamiltonian for stationary eigenvalues and eigenvectors, and then seeing the time evolution of the same. That is like the recipe that you follow for everything. And then once you are doing measurements, then you collapse the wave function on a specific basis set, which we today talked about, that you do basically change of basis whenever you are performing a measurement. Uh, and when you are performing a measurement, of course, there is uncertainty principle directly inbuilt in that, because if you are performing a measurement of, let's say, a position, then you cannot uh, measure position of the system without disturbing the system by changing its momentum by some value. So this is how like X and P are related. This is similarly how energy and time are related. This is similar to any measurement. You can't do any measurement on any system without disturbing the system. That is like the crux of uncertainty principle, and which is inbuilt in the measurement process. And the measurement process in the quantum physics is always probabilistic. So we will always talk about probabilities, and we will never talk about absolute values because there is the experiments that happen in quantum physics are not deterministic experiments. They are always probabilistic experiments. And in terms of lasers, you're also required, or it is useful to know all the distributions that are possible. So there are like different states of light that are very commonly used in the light matter interaction formalism, which is one of them is Fock state, another state is thermal state, and third state is coherent state. We talked a little bit about those states whenever we are doing the introduction for the topic, but I will talk more about them as the course progresses, and whenever I think it's the correct point to talk about like three specific states of these photonic statistics. So these are like the three states: Fock state, coherent state, and Fock state, coherent state, and the thermal state. Yes, the thermal state, which is thermal state gives you the incoherent source state. Then coherent state, of course, gives you the coherent state, which is the light coming out of the laser, and the Fock state, which is the number state, which we are going to use as well for light matter interaction when we are doing a quantized version of the electromagnetic field. So light also, we also motivated that light we can imagine in terms of either photons, or we can imagine light in terms of electromagnetic wave. If we are imagining light in terms of electromagnetic wave, then that is a classical formalism. And if we are imagining light as the photons and the number of photons, then it's a quantum mechanical formalism. So we can do light matter interaction either by keeping even the light, even the atom as classical atom, which is classically we imagine the atom as a dipole, and in quantum physics, we can imagine atom as a two-level system. Then, if you are considering light, light can be imagined in terms of electromagnetic wave or photons. So you can either treat both of them as quantum systems, you can either treat both of them as classical systems, or you can treat uh, atom as a quantum mechanical system, which is two-level system, and the light as a classically electromagnetic wave. And if you do this formalism, then it is called as a semi-classical formalism, where you treat the atom as quantum mechanical and the light as classical. So that's why it's called as semi-classical, because one of the two is quantum. So that's why this is the formalism that we are going to follow. That we will imagine atom as a two-level system, and we will also imagine light as an electromagnetic wave at the start, and later we will motivate that light can be thought of in terms of harmonic oscillator, which gives you now the second quantization thing, and that incorporates both of them as then quantum particles or quantum formalisms. So for that, today's lecture was also important because we will be dealing with many particles later when we generalize our system. But even when we have a single particle and two states, which is like the two-level system, still density matrix formalism is pretty useful because you can already now have an idea in your head that there is a matrix. For two-level system, there are just four matrix elements, and the diagonal elements gives you the population in state one and state two, and the off-diagonal elements gives you how much of these two are correlated. What is the correlation between the first state and the second state? So that's why the density matrix formalism is really crucial to understanding the derivation for light atom interaction Hamiltonian and solving that Hamiltonian as well. So I think in the next lecture, we will start with the light matter interaction finally, because I mean, I guess I didn't plan the lectures to be this long before we reach this derivation, but I think the background that I gave or the background that we discussed together was kind of necessary to all for all of us to build up to this light matter interaction or light atom interaction Hamiltonian, and to study and to solve this system. Because if we directly solve this system, if we directly go on it without this background, then it will be very difficult for us to motivate, or it will be very difficult for us to understand each step. But now that we have spent so much time on studying different aspects of this formalism individually, we will now not have a really hard time to understand the entire derivation that is given in the seventh chapter of Foot. So I think in the next lecture onwards, we will start with that derivation. So that's why I wanted to keep this lecture as like a short lecture compared to the earlier lectures that we had. I will also provide you some additional material that is there in addition to the seventh chapter of the foot book, which will help you understand, which will help you visualize how this interaction takes place. There are some really good lectures as well, which I have already told you about, but I will still emphasize on that in the next lecture, and I will give you the resources. We will, after that derivation, we will also do programming, and we will visualize systems for that same solutions. And then we will see how light atom interaction is used for the research that is happening right now in the everyday in like the most leading research labs in the world, and that will, I think, motivate you, that will convey nicely the importance of this topic. So I think with that, I think today's lecture is almost done. Uh, as far as what content I wanted to cover, it is like I just took an hour of class today, so it is little shorter than usual. But if you guys wanted to discuss anything before we go to this derivation, which is like the main derivation for this course, um, you can, oh yeah, you can always talk to me. You can talk to Nitin sir. If Nitin sir wants to take any other topic before we go, before we move forward to this derivation, then I'm also up for that. But if not, if no one has like any doubts, or Nitin sir, if you want to say something, you can say, because like this is the only topic that I wanted to cover in today's lecture, and as far as that is concerned, that topic is done. So I think this is enough background now for us to go to the main derivation. But if you want to say something, or if you want to add something to whatever I have said already, then you can. But this is, yeah, and please do the assignment that derives the four properties for density matrix. Um, yeah, if you want to solve problems, then you should solve problems. If you want to take like one problem solving lecture with the students, then I guess you can take that. So, I mean, the reason why I don't want to take like a lot of problem sets while I'm doing lectures is I can give you assignments, and then mostly whenever it comes to problems, I generally believe that the problems have to be done just by the students, and whenever they have doubts or whenever they are stuck at some problem, then definitely we can help uh, while lecturing. But yeah, so if you want to take any problems sets, or if you want to familiarize yourself with density matrices, then you can you can take maybe a week. So if we can even take a break next week, in the sense that we will not start the derivation right away. So next week, if same time, if someone else, I think Krish, Krishna Sri, Krishna Sri, if want to do the problem solving session, then maybe they can go ahead and they will do that. So if you want, then next lecture we can do that problem solving session, and after that section is done, after that lecture is done, then after that session is done, then we can start with the light atom interaction, because maybe you guys will feel more comfortable after doing some problems with density matrices. So I think that's a great idea. So okay, I guess then in the next lecture, maybe same time, or you guys can coordinate with Nitin sir. They will conduct a problem solving session based on whatever we have done till now in like 5 lectures, mainly I guess density matrices, because that is like the new concept that you guys have learned here, which was not introduced earlier. So I guess that's a good plan, that maybe next Saturday, then you can have that problem solving session, and the Saturday after that, I will again take a lecture, in which I will definitely start with the light atom interaction, which is the seventh chapter of uh, the foot. So, okay, so people can coordinate with Krishnasri, and Okay, I guess in that case, like that is all I wanted to say on this like topic before the derivation starts. So maybe see you guys in the in next to next Saturday again. That Saturday I will take the lecture and start with seventh chapter input. So I guess thank you for joining. If Nitin sir wants to say something, I don't know. Uh, Maybe he can, but okay. I guess then this concludes the lecture. Thanks, I guess, for joining.